Yeah, over here I can't use the pen, so let me just. Okay. Oh, sorry. No, what happened? Yeah. Okay. Yeah. So, yeah, okay. So these are the compatibility graphs. Now, so what we need to find is we need to find a closed set of compatibles. So, so in the compatibility graph, we need to find a closed set of compatibles. All right. So let us try to find a closed set of compatibles. Now, what you have done is over here. So maybe we can refer to this also. So here we have found some a number of closed set of compatibles. Okay. So we can. So here we have taken. If we take only CE, if you take only CE as you have seen here, if you take only CE, so or maybe yeah. So here you have the closed set of compatibles. So here if you take only CE, CE as you can see is the standalone compatible. Okay, you can, and then you can choose not to merge anything else. I mean that is one option, and that has a cost of 5. Now here, if you look at another, uh, you know, another option. So here again, so here AB is taken, all right. Now once you take AB, of course, you have to take EF, you have to take CD, and you have to take BC also. So, and as you can see, all the 6 states are covered. Okay, if you take this 4, all the 6 states are covered. So, so this is a closed set of compatibles. If you take these, you don't need to take, oh, you need to take AC as well. BC depends on AC, so maybe this is not correct. You need to take AC as well, isn't it? So maybe this is not correct. There is a problem with this. if you take BC, you also have to take AC. So this is not correct. If you so if you take these, as you can see, the transitive closure of AB includes AC. But interestingly, you find that AB, BC, and AC. So so if you take this, what you find is that you have a clique over here. Okay, so if you see AB, no, so yeah, you have AB, BC, and AC. So together you have a clique. All right. So in fact, the closed set of comparables what you have here is ABC and then EF and then CD. So this is what you should have. This line is not correct. Okay. So when you take this, you know, this is what you get. So these are the cost of 3, as you can see. Now, if you take, so you can try consider this. So here, if you take DE, so if you take DE, you find that you got to basically take a lot. So DE means you got to take. So can you trace this graph and see and tell me, one of you, can you tell me, if you take DE, which other comparables you got to pick as well? Okay. If you take DE, so if you take DE, you find that you got to take CD, you got to take CF. Now once you take CD, you have to take EF also. So from CD, as a result of CD, you got to take EF, and as a result of taking, so you have, and then you got to take BC, and you also have to take AC. All right. So you need to take these. Okay. So this is a closed set of comparables. So do you have any clique over here? Let us see. Now if you take a look at this, CD, DE, and no, so you don't have any, I don't see any clique over here. Okay, so I'm not seeing any clique over here. All right, so this, as you can see, it has a cost of 6. Okay, it has a cost of 6. So you get 6 states over here. Now, so we're just finding some closed set of comparables. You can look at, yeah, now this is one set. Now if you add to this, so you have got BCAC. So if you add to this AB, you can add AB to this, because in that case you get a click over here. So if you add AB to this, the cost comes down to 5. So that is what is shown over here. So this one is ABC. Alright, this one is ABC, and I think C, yeah, and if you add to that, I think CE, suppose you add to that CE, so you have CD, DE, and CE. So here you have another click. You can form this. So if you consider CE additionally, then the cost comes down along with AB. Then the cost comes down to 4. So these are various closed sets of compatibles. Okay, for the machine ME. Alright, for the machine ME. Now, alright, so is this okay? I mean, this is a pure graph operation. We have just considered closed set of compatibles. So is this okay? Have you been able to follow this? Yeah?
Sir, by adding CE, we have one more click, sir.
Sorry?
By adding CE, we are getting one more click here. CE, EF, CF.
You're no, just 1 second. Maybe I should increase this. Yeah, come again.
By adding CE to this set, we are getting CE, EF, CF also another click, sir.
Oh, you are. Okay. Let us see. Okay. So, okay. So that will probably help you. So CE, EF, and CF, is it? Okay. CE, EF, and CF. Yeah, that is right. So let us see. Yeah. So okay. Yeah. So if you do that, of course, then the cost comes down to 3 again. All right. So these are various. So in that case, you have this thing. CDE and CEF, and you can see ABC. Okay, yeah. So that is also possible. Now, now let us try to do. So suppose we consider this one. Suppose we consider this one. All right. So let us see how we can design the machine. So this is ME. It is useful to go back to ME. Okay. So this is you have there the finite state FSM specification of ME, and this is our so this is a reduced this is a closed set of compatibles for ME. So let us so ABC, okay, if you consider the the merger of ABC, So let us see what happens if you are considering the merger of ABC. So so when you are merging ABC, so what you are saying is that we just give it a name. So ABC, we are giving it a new name. We're just calling it alpha. Okay, we're just calling it alpha. So these are, as you have seen, these can be compatible. That is how we have constructed the graph, or the merger table from the graph, the compatibility graph from the merger table. So in this machine, you have got two inputs, I1 and I2, and so let us see what happens when you get I1. So as you can see, the transition on I1 should be to states E and F, E or F, it can be to any one of those, right? So let us just write ABC, then you have EF, or if we just do it the way it has been done here. So let us just call this beta and this is gamma. Alright. So if you consider the transitions of the states of ABC, which we're calling alpha, on I1, as you can see, you can go to E or F. So that is, it should be to gamma. Alright. And the output, you can see from the table, should be 0. So that's all right. And let us consider the transition on I2. So on I2, let us see. So A goes to B, B goes to A, and C goes to C. So that's all right. So it comes back to gamma, and the output is also 0. All right. Sorry. I made a mistake there. It's not to gamma. It's to alpha. It's to ABC. So the output is 0. Let us consider CD. So CD on input, getting the input I1, so it goes to either E or F. Alright, so E or F, that is gamma. Alright, it goes to gamma, and the output must be 1. Alright, must be 1 because the output of F is 1. Alright, and on I2, okay, on I2, so for CD on I2, it goes to C. Now look at this, it is going to C and D is going to D, right? So if you look at this, there is a interesting thing that's happening. So C is shared. C is shared between these. All right. Now, when you are considering the transition on I2, you are seeing that you have a transition, back to CD. So you can, C and D. So C and D. 1 second. I've called it gamma. Why have I called it gamma? This is a little strange. I am going to CD. So So I think it should be beta, and the output should be 0. So what you see is that so this component, I think there's a mistake here. So if you consider the transition of this is ME, right? Yeah. So if you consider the transition of CD on input I2, it's to C and D, it's C goes to C and D goes to D. So this should be beta really, not gamma. And here, so if you look at this, uh, we are really splitting C into two states. So we are splitting C into two states. So C is, this beta, the C in beta is one incarnation of C, and so you can think of this as C1 and C2. So you have really split. You have, so here you can think of this C as C1, and you can think of this C as C2. So you have really split C into two states. So if you think of the transition of C, C1, so really, if the transition of C1 on I2 is C1, an output of 0, and the transition of C2 on I2 is going to C2 on 0. Alright. Now let us see EF. So EF is going to CD, right? So EF is going to CD, which is beta. Oh, 1 second. I've used different symbols actually. I think that's the reason we are having this problem. Alpha, gamma, and delta. I have used alpha, gamma, and delta. Oh, sorry. Alright, so I think that's the reason we are having this problem. So what was it before? Let us just review it. So rather, we are keep calling it delta, and we are calling this gamma, and this is delta. All right. So yeah. So that's why this is actually not wrong. Instead of beta, we can call it and this one, instead of all right. So yeah, sorry about that confusion. So let us consider so here what you can see is that Yeah. So C2, when you get I2, you are, you know, going back to gamma. So that is C2, you can say. So this is C2, and this one is, we like to put in blue, this one is C1. Alright. So let us see what is happening with EF. So with EF, we are going to CD. Alright. So CD here is gamma and the output is 1. Alright. And if you consider gamma, gamma means, so in other words, this transition, so if you look at the constituent transition there, if you look at the constituent transition there, so C is going to C2, C, so E is going to C with an output of 1. So we are going to, it is making a transition to gamma, which is the C2 incarnation of C, you can see, the C2 version of C. So it is going to C, and here it is going to CB, alright, so or BC. So BC is, as you can see, alpha, and the output is 0. But this alpha, you can say that, so here it is going to C1 with an output of 0. So what you have essentially done is you have split the state C into two states, and you have so essentially you can see how the splitting is happening, because C is, you know, there in two clicks, so it behaves a bit differently. Okay, it behaves a bit differently. Of course, the outputs are same. You can see that C must always have an output of 0 on I2. So both the incarnations have outputs of 0 on I2, but the transitions are different. So this one is making a transition to the C2 version, and this is making a transition to the C1 version. Okay. So what we have here is, so that's an interesting aspect, as you can see, of the optimization, the optimization of incompletely specified FSM. You have state splitting, all right. You have state splitting. So yeah, so this is the reduced FSM. So now, after you have this reduced FSM, let us see what you have after this. Okay. So why don't you do one thing? Why don't you take up MD? You can just take it up as an exercise now. MD. So this is the compatibility graph for MD. So why don't you work this out yourselves? Why don't you, or I can show the compatibility graph of MD here. Yeah, this is the compatibility graph of MD, and MD, the machine MD is shown over here. So why don't you why don't you do this on your own? You can do it right away. Yeah. So please work out uh, the optimization. So find out the closed set of compatibles for MD and then construct the reduced FSM for MD. Yeah, please do it now. I think you can first copy down this the spec for MD and this compatibility graph in your notebooks. Just check that there aren't any mistakes. So you can copy this down in your notebooks and then you can form the closed set of compatibles. You can try to form various closed sets of compatibles. Alright, so please do it now. They are already doing it, so you can show it after some time. You can you can do it and post it here, then in the chat box. Then I can take a look from the chat box. Okay, so has anyone posted? Yeah, anyone could do it or not? Huh? Chandan, are you there? Did you do it?
No, sir, not yet.
So, what's the problem? Could you find a close set of compatibles at least? Yeah? Hello? Chandan?
Sir, actually, I didn't copy it. Means,
You didn't copy it, but it was there on the screen only. It was visible, I think.
yeah, okay, means I was copying it and then I was doing it.
Yeah, I had kept it visible anyway. So, who is there? Pranav Rajput. Could you find a close set of compatibles? Pranav, are you there? Hello? Aryan? Aryan Singh, are you there?
Yes, sir.
Yeah, did you form the close set of compatibles?
I formed a group, but I don't know it's a minimum or not.
Okay, at least, so you can at least find, you can at least find some close sets of compatibles. Okay, so Srijan has posted, yeah, so some of you have posted. So let us just, okay, so let us just, yeah, okay. So we can compare this with, maybe we can compare this with, this is, this is for MD, I hope.
Yes, sir. MD.
Okay, so let us just compare this with the. So what you have done is, okay, you have got a table. Okay, first one is trivial. Second one is BD. So BD is standalone. You can do it that way. And third one is AC. So if you take AC, let us see. So if you take AC, you got to take CF, of course. And then if you BD is standalone, and then you're taking just E. Okay. So that's an option. And the other one that you have done is AD, BE, and CF. So let us see. AD, BE, and CF. So have you covered everything? The AD, BE, and CF. Okay. Okay. So you have covered everything. Yeah. And this, yeah. So there are some other options also. So Srijan has posted BC, EF, and E, and Shomita has posted yeah, okay. So I think is this the same one that you had done? Where is that? Okay. So this is AD, BE, and CF, and she has also done AD. Oh, okay. So that's interesting because she has taken AB, CD, and EF. So AB, CD, and EF. Okay. So yeah. So what you can see is that many closed sets of compatibles are possible at a cost of 3. Okay. At a cost of 3. And this is the reduced machine. So let us inspect the reduced machine with respect to the this table, the FSM table. So A and B, okay. So A and B is called alpha here, and here your so this transition is to E. So E is contained in EF. So one thing about this is that there is no state splitting involved. So this one should be quite straightforward. In fact, this one there is no state splitting involved, or the sets of states are disjoint. So this should be pretty straightforward. All right. So let us just check the rows. We should be able to check the rows also quite easily. So for AB, so you're going to E. So E is contained in EF. So you're going to gamma. Then if you consider the transition of AB on I2, you're going to C. So that's beta. Then E, that is gamma, and this is B, that is alpha once again. So let us consider for CD. So CD, you're going to, yeah, okay. So Shobita, one point to note is that, once you're when you're minimizing the machine, so the machine that you have proposed here, this is not implementable as yet because this part is not yet known. All right. This part is not yet known, so you need to specify it. Because if it is left unspecified, you can't implement it. So you can specify it to your convenience, of course. So this is a don't care. So you could, for example, send it back to beta. So you could, send it back to beta, and maybe the output function could be kept as 1. So that's a possibility. Okay. That's a possibility. So you do need to specify it. You can't leave it unspecified if you want to implement it. Okay. So let us look at. So this one is also disjoint, so should work out similarly. Here also, Aryan, you have left this unspecified, so you don't need to specify it. So you could specify it as so yeah. So what would you? Okay. So let me ask you, what would you like to specify this too?
Alpha comma 0.
Okay, alpha comma 0 is possible, of course, but let me just you know tell you, I mean, just sensitize you. See, the choice, although you can make an arbitrary choice because it is left unspecified, but your decisions, the decision that you make, it does have a cost implication. So ultimately, as you know, you have to, I mean, this functions have to be implemented using gates. So it is maybe advantageous to specify so that the cost of the implementation is reduced. So if you make the output as 1, then you find that all the outputs in this row would be 1. So that's a don't care, you know. So that means if you keep it as 1, then whenever the state is alpha, the output is 1, irrespective of the input. So it becomes a don't care on the inputs. So you would definitely like to specify the output as 1. And the next state, you know, so if I1 and I2 are adjacent, for example, so you might like to put it as gamma, because then if you think of, you know, the way you minimize the functions, if you keep it as gamma, it'll be, it's likely to be, you know, easier to, that will be easier to simplify, or, you know, the cost of implementation could be reduced. So as compared to alpha, gamma might be a better choice. So here you got beta. All right. So those are, but it's not easy. You know, those formulations aren't easy. So there are techniques which consider, you know, making these choices, but those are not easy. But at least you should be sensitized to the issues that are involved. Okay. So that's a point to note. All right. So I think Srijan, you have you know, um, suggested B, C, D, E, F, and A, B. So actually, I would. So have you done this minimum? Have you constructed the minimal machine? Because I would like to see your solution, because you know, B. So here your solution involves state splitting, as against their solutions which do not involve state splitting. All right. Yeah.
Yes,
Someone
I
is.
face confusion there is when the output state is B, so which input to take, BCD or AB in that case?
All right. So let us try to do it and see what you get. So B, C, D, E, F, and E, B. All right. So All right, so let us see what is happening. So BCD, so BCD on I1, both are going to EF. So that should of course be beta, and the output should be 0. On I2, it's going to F, sorry, BCD, right? Yeah, so C is going to F, so which is covered only by beta, and the output is 1. And this one is covered by B. All right. So, okay, BCD. All right, BCD. This is okay. For the time being, I'm just
So
leaving
here I
it.
am facing
Sorry.
confusion whether it is a BCD or AP.
Sorry.
So when on input I3, if my
Yeah.
present state is BCD, there whether my output state will be alpha or gamma, there I am facing the confusion.
Yeah. So let us see. Let us see. So when you have I3, so you are considering BCD. All right. So I mean, it is going to be right. So I mean, suppose you keep it as let us say that you keep it as BCD. So that is alpha, right? You uh, you can keep. So you have two options. So you can keep it as alpha with an output of 1, or the other option is that you could also keep it as gamma. All right, so let us just alpha or gamma, and the output is always 1. All right, output is 1. So let us look at EF. So EF, that is C, so that is C is covered only by, and the output is 0. This is on I2, it is F, which is beta, and the output is 0. It's AB, comma, and the output is 0. And this is CD, which is alpha, and the output is 1. And AB, okay. So AB, the output is E. So here, of course, there is no confusion. And yeah, AB on this is C. C is covered only, and the output is 1. And here you have AB, E, beta, and the output is 1, and this is B. So here again I changed AB, so it is B. So you have the option. You have the option of either alpha, the output will be 1, of course, and you have the option of beta, right? So B can be either this two. So I hope, yeah.
It should be gamma, sir.
Oh, sorry, it should be gamma. Yeah. Yeah. So does it really make any difference? Let us say. Suppose you choose it as alpha. If you choose it as alpha, you get a loop. If you choose it as gamma, you just have a transition to this. I mean, so does it make any difference? So I think either option is okay. This one you got to specify. So if you take this as, so this one could be, made the same as this, whatever you choose here. So it could be just duplicate. That might lead to a less expensive machine. Whatever choice you put here, the same choice you put here. And here, so here you have so if you want to, so here if I2 and I4 are adjacent, then it is better to choose alpha if I2 and I4 are adjacent. Otherwise, you can then maybe choose gamma. So so it doesn't really matter much. It doesn't really matter much. Okay. So these are the options available to you. Okay. So yeah, so that is what you have here. Okay. So this is how you can minimize your incompletely specified FSM. So you got to find this closed set of compatibles, and those might involve state splitting. All right. Okay. So that is about it, I think, in the slides. Okay. So yeah, you have got some. See, so over here we have given implementations for ME and MD. So I think you should just try to do as many examples as you should, of course, do all of these, and maybe some other examples also. All right. So that is about the minimization of incompletely specified FSMs. We have got, maybe we can we have to look at flip-flops, and we also have to look at asynchronous FSM. So maybe we can just look at this is yeah, we can look at asynchronous FSMs, and then we can also look at some flip-flops. There are, I mean, so far you have studied only the D flip-flop. There are some other flip-flops also. We'll look at those. So so let us just look at asynchronous machine design. So so far you have been looking at synchronous machine design. So the important aspect of synchronous machine design is that you have a clock. Okay, so you have a clock. So let us say that So this is your, rising edge of the clock. This is the rising edge of the clock, and this is the falling edge. All right. So depending on the kind of flip-flop you use, so some flip-flops transfer data on the rising edge, some flip-flops transfer data on the falling edge. I mean, that depends on the design of the flip-flop. So what happens is your next state function, so if I put dash indicating the new value of the next state function, all those, so if you look at this, okay, one thing that we did not do, so maybe we should just do that. So let us just take up any one of these. The next thing, of course, this is a symbolic table. This is a symbolic table. So let us take up ME, which is slightly simpler. So we have taken up ME, okay? So so when you consider so you have to actually do something called state assignment. That means you have got, let us say, alpha. I'm talking about ME. So you're talking about, you've got alpha, gamma, and delta. So what you got to do next is you got to do state assignment. So alpha you can assign. So you have got 3 states. So you'll need 2 bits to encode those, right? So I could encode alpha as say 0, 1, beta, or maybe I could just encode as 0, 0. So let us call this 0, 0. This is 0, 1, and this is say so I can choose this either 1, 0 or 1, 1. So maybe I could choose it as this significant bit as 1 and this is don't care. So I could actually consider both. So let us look at this. So on I1 and I2. So I'll consider only the next state function. Actually, of course, I should consider both the functions. So this one is gamma. So let us just call this, let us say 1, 0. So if I say that this is delta, sorry, this is delta. So the next state function, this one will be 1. Actually, this is this 0. So let us see whether we can. Okay, let us just do it with 1, 0 first. 1, 0. This is 0, and this is alpha. So this is 0, 0. This is maybe I can just write it here. This is 0, 0, and the output is 0. And here it is delta, which is 1, 0, and the output is 1. Here it is gamma, which is 0, 1, output is 0, and this is gamma, which is 0, 1, and the output is 1. Alpha is 0, 0, and the output is 0. Output is 0. All right. So now so here I could actually not care about this bit. So I can say, so this is say S1 and S0, right? This is S1 and S0. So all I need to focus on, because both are 0 here, I only need to focus on this. So if you see that, so I really don't need to bother about S0 when S1 is 1. So I could leave it as don't care, I could. So if I leave it as don't care, basically what I'm saying is this is both 1, 0 and 1, 1. So I'm allowing 1, 0 and 1, 1, both 1, 0 and 1, 1 to represent the state delta. So because I really don't need to bother about this. I don't need to bother about this. When S1 is 1, I can just, I don't need to look at S0. So so I can generate this function. I can generate this function. So here, when I'm generating, when I'm generating this, so here this output is really don't care. I can leave this output as don't care. All right. So that way, when I optimize the function, I just have some additional scope for carrying out the optimization. All right. So is that okay with you? Do you understand that? Yeah. Hello. Okay. So
Yes,
this,
sir.
yeah, this is called state assignment. Now, the point to note is that suppose I code this as 1, 1. I mean, just suppose that I code this as 1, 1. So just suppose that I code this as 1, 1. All right. So in that case, the output here is 0, 0, right? So in other words, what I have is I was not using delta actually for a reason, because delta is usually called the state transition function. So maybe I'll just rub out delta and I'll use some other, I'll just call it beta, that's all. So here I know that delta and let us say I2. Of course, I2 also you got to, I've left it symbolic, but you got to code this also. So that is actually, input encoding. So this one is 0, 0, right? This is 0, 0. So in other words, this, if you think in terms of flip-flops, if you think in terms of your flip-flops, so really you have two flip-flops there, isn't it? D0 and D1, and then you have some, this is the next state function, all right? The next state function, so this is going into your next state function, and you're getting new values, right? You're getting new values for D0 and D1. So this is S0, S1, S1 dash. And very important is that you have the clocks here. Maybe I can just denote the color. All right, now if you look at the, so what is happening is, I mean, suppose this is, just suppose that, in a transition at neg edge. I'm just making an assumption. It could very well be at the positive edge. It's just an assumption. So now, you have let us say S1 dash, and or let us say that, let us just put it a little differently. So let us say that S0 and S1, you got S0 and S1 at this time. And then in course of time, okay, in course of time, you got S0 dash, and in course of time, you got S1 dash. All right. you got S1 dash. Now, in this particular case, it is, let us say, let us just put this from 1 1, you got 0 0. All right. Now, you have got 2 bit changes. So the actual transition, probably it could have happened that, you know, so let me just put it in one line. So maybe it was 1 1 and then it became 1 0 and then it became 0 0. Or now, when you have the synchronous design, doesn't matter. Doesn't matter. Why? Because these intermediate changes don't get reflected because the transition happens, maybe the transition actually happens only at the neg edge of the clock, right? It happens only at the neg edge of the clock. And that is probably long after this, you know, the values are stabilized. Okay. This is long after the values are stabilized. So there is an advantage of the synchronous design. So what is an advantage of synchronous design? So let us just write. Synchronous design. So what is an advantage? Not intermediate bit values of NS also inputs. Because as you saw, so essentially what is happening is, you know, you got so you got, let us say, this intermediate values. And then you got this stable values. And finally at this point you got, sorry, I just made a mistake here. This intermediate values is somewhere over here. The intermediate values. These are your intermediate values, and These are your stable values. All right. So, and this is where, transfer at this point, they are in updation of state variables. And okay, so this is the advantage, and the disadvantage. Disadvantage is that it is slow. Okay, it is slow. Wasted time. So much of time is wasted. And advantage is that, you don't have to bother about those intermediate values, but so much of time is wasted. Of course, you can reduce the wastage by making the clock, you could use a faster clock. Okay, but there are other issues with speeding up the clock. You have other issues. We'll study those issues when we look at flip-flop design. So you have a disadvantage. You have wasted time. So one option is one thing to consider is, can we not do away with the clock? So that brings us to asynchronous design. Okay, that brings us to asynchronous design. So that is what we are going to look at here. So here, look at this table. So this is your state and this output. So here you find that we have got some states in blue, which are bold, which are in bold. So let us see how the states are behaving. So the state 1, on input 0, 0, it continues over here. So these are stable states. The state 1 is stable for input 0, 0. The state 2 is stable for input 0, 1. State 3 is stable for input 1, 1. State 4 is stable for input 1, 0. State 5 is also stable for input 1, 1. All right. Now see, we assume that, let us assume that only one bit, assume changes at a time. Okay, you assume that only one input changes at a time. So here you got 0, 0, so it can change to either 0, 1 or 1, 0. So if it changes to 0, 1, the next state is 2. So this state, it settles down to 2. So 2, it changes to 2, and then it remains stable at state 2. Now, and on the other hand, if it changes to 1, 0, it changes to 4, and then it stabilizes to 4 first input, 1, 0. But look at the behavior here. Suppose you are in state 2, all right? So let us see what happens. You could, so say you're in state 2, and here you're in state 4. Now, the input is changing by 1. Here from 0, 1 it is changing to 1, 1, and here from 1, 0 is changing to 1, 1. So let us see. So from this state, from the input 0, 1, if it changes to 1, 1, that means if your earlier state was 3, or was 2, and then it changes to 3, and then it settles down to 3. Okay. On the other hand, if your state was 4, from 0, 1, if it changes to 1, 1, it changes to 5 and settles down to 5. So you're approaching 1, 1 from two different places. You're approaching 1, 1 from either 0, 1 or 1, 0. So in 0, 1, the state 2 is the stable state, approaching this. Now, in 1, 1, of course, you've got two stable states. So there, what happens is, if the input changes to 1, 0, you go to state 2. If it changes to, if it changes to 0, 1, you go to state 2. Changes to 1, 0, you go to state 4. Okay. You're essentially, this is your transition table. Okay. This is your transition table. All right, I think just get the idea of this. We'll continue with this in the next class. All right, then we'll stop here now. Okay. Yeah, Ravi, I posted something. So Ravi, did you want to discuss anything about what you posted?
Nothing, sir. It is very similar to Srijans. B, C, D, E, F.
Okay. All right then. So I think we can stop here now.
Sir, I have a doubt regarding the lab experiment.
Okay. What is the doubt?
Sir, how to make the control line switch after one exactly half cycle and then again make it to one?
You don't. Just if you see what I explained right now, you have to work with. You don't change in the middle. You assume. So let us say this is your clock train. You have to do your design so that you either make a transition over here, you either choose this, or you choose this. Any one is fine. Assume that it will change. Either your states will get updated either at the rising edge or at the falling edge. It doesn't change in the middle. All right. So you have to, yeah, you got to choose. You got to choose one of these two options. You got to choose one of these two options, either this option or this option. So there is no, so you don't have, in between, you don't have any transition. You don't have anything to do in between this.
sir, but how to do this? But we are not able to use a transition table, proper transition table.
No, see, what you have to do is it's not so difficult. See, you have some flip-flops because you're double. The way it works is I'm just drawing them in two colors. I mean, these are your inputs. I'm just saying that you're giving your inputs here. Okay, so your inputs. So this is parallel load, and then you transfer serially. All right. So these are your input bits. And this is your, what you can just say. All right. So now what you're saying is that you have a conditional adder, right? So if you're adding, right? If add I'm just calling this the nj. Add 3 if nj greater than or equal to 5, right? So normally you're going to shift. So you have a multiplexer here, right? So normally you're going to shift. So what you're doing is you're either so when you shift, you either take the output of this. So the output of this, you've got a 4-bit output, right? You got a 4-bit output. So now you consider, so this will get the input either from here or from here. All right. So if you get the input, so you can just have, so similarly over here, you'll either get the input from here or from here. All right. And the basis of the selection is basically, this is your, nj greater than or equal to 5. So if nj is greater than or equal to 5, if nj is greater than or equal to 5, this is nj greater than or equal to 5. This is a status indicator. All right. So it indicates whether nj is greater than or equal to 5. So if nj is greater than or equal to 5, you have already added 3. So you should take the output from that, and the output goes to the next bit because you are shifting left in every step. Okay. So the input here is either from the previous bit, if so, basically, of from previous bit, if nj is less than 5, and from adder, if nj is greater than or equal to 5. So that's all. It's as simple as that. Okay.
Yes, sir. But
Hmm.
for the left side orange color register, we have this condition that the control line will be nj greater than or equal to 5. But for the right side,
No, that just decides the source of the bit for for these 4 bits. This one decides for these 4 bits because this output will this output. So you have a multiplexer here. You have a multiplexer here, which will get either from here or from here. And here you'll have a multiplexer which will get either from here, here. And this one always gets from, the previous one. Previous one means you could have another such block. If this is the rightmost bit, then of course it will get it from here only. Otherwise from a similar circuit on this side. Yeah, so all of these 4 bits are controlled by this.
yes, sir.
These 4 bits that's it.
Yes, sir, that is fine. But for the input, there is a register for the input bits also, right? At the right, at the whole right thing.
This one, you mean this part?
Yes, sir. For that we have to set the control line such that in the first cycle the input bits from the parallel input will come, and then on it will go on.
This is at the beginning. This is at the very beginning. At the very beginning, you got to load some value in this. You got to load some value in this, and then you just so this will happen at the very beginning. At the very beginning, you are going to load some value into this, and beyond that, you will have. So here also you have serial. So what happens is at the very beginning you load it in parallel, and then beyond that you just do shifting. So parallel loading at the beginning. Okay, this parallel loading at the very beginning, and then you just keep shifting left. That's all.
Yes, sir. And that the behavior of the right side register has to change, right? That it has to shift other than taking the parallel loading. That thing we can do manually, right?
Yeah.
Yes, sir.
Then
That's that.
actually, you can also do it using a finite state machine controller. So you can your controller is basically the initial. You can do it manually, but that's fine. But you can also design a controller, because after all that's an FSM. So at the very beginning, what you will do is you will load it, and in the subsequent states you will just keep on shifting. That could be a simple finite state machine. So you could this is, I mean, when you do counters you will be able to do it better, but you can say that this controller works as follows. So here you can this is a initial state. So here and you can just shift. So this is parallel load. And this is left shift. Okay, so this is without a counter. So this will just keep on shifting. But if you have a counter, which you will do after, later on, then what you will find is that after, you can count for example, if it is a 8-bit, or 7-bit, whatever. So you can count 7, and then you can maybe I'll just put it. So you can again come back here, after you finish the count, after finishing the count. But at the moment we have not yet done the counter, so maybe you can just after we do the counter, you can just incorporate the counter into this part. So then it will be more interesting. I mean, then you'll not have to do it do this part manually. So for now, you can just do it manually, or you can just have a simple. Of course, if you do it like that, what will happen is that you'll have to stop the clock manually. Otherwise, it will just keep on shifting. It will not stop. Okay.
Yes, sir. Yes, sir.
So you can, I mean, this much you can design now. This part is powerful. This you can design now. So in this case, you stop the clock manually.
Sir, also there is a problem in designing in this state machine also, because that flip-flops also have to get some initial value, right? Not from the combinatorial cloud. That they
No.
have to be initialized first of all.
You just check if you it should, because if you look at the design after the clocking is done, your inputs will override. So your initial values could be unknown. I think it will work that way. Your initial values would be unknown, but once you start clocking the values, your values will become known. Okay. So
Yes.
so that should not matter. So you just check on that. It should not matter.
But in this circuitry, that thing we are getting there, if nothing is given, that is taking in crosses. That means that it is taking as a don't care, and
Yeah.
then on adding or
No.
doing
No,
anything, it is not giving the correct values. It is
if you add, of course you will not get because if you are adding, then you will not know. Yeah, of course you have a problem, because if you have unknowns, then that adder circuit will create a problem, because then you cannot compute whether it is greater than or equal to 5. That you cannot compute actually.
Yes, sir.
So yeah, so actually in this state, in the initial state, you can also parallel load all the other these bits. These bits you can parallel load all of them to 0. Okay. You can parallel load all of them to 0. You can or you can use a synchronous reset. You can use so that you have a synchronous reset bit, right?
Yes,
So
sir.
you can do a synchronous reset of this flip-flops to 0. So yeah, because as such a shift register can shift, that is not the problem. But in this case, you have another circuit here, which actually looks at all these values. So if these are unknown, then you'll have a problem with this. The outputs will also be unknown. All right.
Yes, sir.
So,
So we can manually switch those things, right? The
no, you
clock.
don't have to, no, you don't have to. Yeah, I mean either manually or if you use this circuit. So in this circuit, not only parallel load and initialize all bits to 0. Then it will be fine. Initialize means via synchronous.
बाद में तो और टाइम नहीं पा, फिर नहीं कटा पाएंगे बाल आज.
All right. So it's synchronous reset. So if you do that, then it should be fine. Okay.
Okay, sir.
All right, then I think we can stop here today.
Yes, sir. Thank you, sir.